AMOS is a cloud-based operating system designed for the future of distributed applications. Instead of a single monolithic system, AMOS is built from independent containerized services, each one acting as its own intelligent software entity. These entities connect, communicate, and work together to deliver powerful and resilient applications. Their relationships and behaviors are modeled in a graph database, giving us a living blueprint of how the system functions as a whole. To build an AMOS application, we start by defining the structure as a graph schema. Entities become vertices, and their communication paths become edges. Attributes are defined in a YAML schema file, allowing rapid and repeatable configuration. With the schema in place, we deploy services into the cloud. Today, AMOS has 4 core components. APM, Autopoietic Process Manager, deploys containerized services and allocates resources. SEM, Structural Event Manager, connects services based on the schema and defines valid communication paths. CNM, Cognitive Network Manager, adapts the network dynamically to keep everything running efficiently. SWM, Service Workflow Manager, monitors for anomalies and triggers redeployment when needed. Together, these components enable applications that are self-deploying, self-managing, and self-healing, the foundation of autopoietic software. After the AMOS schema is defined, we can deploy our first instance using the Autopoietic Process Manager, the APM. The APM takes our YAML file configuration and launches each containerized service entity, assigning its container image and resource requirements automatically. Whether we're deploying to a cloud provider or running locally for testing, the APM gives us a consistent process. With a single YAML file defining the requirements for the AMOS application, deployment becomes fast, repeatable, and hands-free. Once the APM completes deployment, the Structural Event Manager, the SEM, takes over. It uses the AMOS graph schema to automatically connect the newly deployed services, enabling only the communication paths defined by their edge relationships in the schema. The result is a secure, structured network where every interaction has a clear and intentional purpose. With our AMOS instance now active, we're ready to deploy and operate a wide range of distributed applications, all managed through the AMOS operating system. The first AMOS application we'll explore is a video on-demand streaming service. This example demonstrates the resilience of the AMOS infrastructure, especially its built-in failover capabilities that keep video streams running even when a service becomes unavailable. Every AMOS application begins with defining its schema. In this case, we model several containerized service entities, each with a specific role. UI service, the user interface where viewers browse and play videos. Customer service, tracks each user's identity and viewing history. Session service, groups viewer actions into session data, providing continuity across visits. Video server service, streams content from an S3 bucket to the UI with automatic failover for uninterrupted playback.
All these services are continuously monitored by the Application Event Manager, AEM, which keeps the graph database updated with real-time status and interactions. This ensures AMOS always has an accurate operational picture, enabling automated recovery and seamless user experiences. With the schema complete, we're ready to deploy our video-on-demand application. Using the APM, we simply provide a YAML file that defines each containerized service and the resources it requires. The YAML also lets us specify how many instances of each service we want to run. In this example, we'll deploy 2 video server instances to demonstrate AMOS failover. If one server goes offline, the system automatically redirects the video stream to the backup instance, preserving a smooth, uninterrupted viewing experience for the user. With the application now deployed, we can begin interacting through the UI. A new user first registers and logs in. At that moment, AMOS creates a customer vertex in the graph database and links it to the UI vertex to represent the start of their session. Once logged in, the user can browse and select a video to watch. That choice is immediately reflected in the graph as well. The customer vertex becomes connected to the video server vertex, responsible for streaming their content. Behind the scenes, every interaction, from login to playback, is tracked automatically in the graph, giving AMOS full visibility into the application's behavior in real time. As the user is watching, we can simulate a network interruption, for example by shutting down the video server currently streaming the content. When this failure occurs, AMOS automatically detects the disruption. The UI immediately switches to the backup video server, continuing the stream without pauses or buffering. The viewer never notices the change. This demonstrates one of the core advantages of AMOS: built-in failover and self-healing behavior, allowing applications to remain operational and responsive, even as services fluctuate or fail behind the scenes. The next AMOS application we'll explore is a predictive credit card default system, inspired by the example in data science projects with Python by Stephen Klosterman. This application analyzes 6 months of credit card activity to predict whether a customer is likely to default in the following month. As with every AMOS application, we begin by designing the structure as a graph database schema, modeling each part of the system as a containerized software entity. UI service allows a user to upload a CSV file containing historical credit card data. Month service manages the timeline of the rolling 6-month period for each customer. Customer service tracks individual customer behavior and financial history. Account service records each customer's account status and credit limit. Billing service monitors monthly billed amounts. Payment service captures each month's payment activity. Default service evaluates payment history using rule-based analysis to determine default risk for the upcoming month. Event service maintains a complete event history across all entities, enabling full transparency and explainability at both the group and individual level. By representing the application as a graph, AMOS provides a dynamic operational view of how financial behaviors influence credit risk, while enabling autonomous monitoring, adaptation, and future predictive enhancements. With our service definitions and resource requirements captured in the application's YAML file, we can now deploy the system through the AMOS APM. To demonstrate an active-active failover strategy, we deploy 2 instances of every containerized service. This ensures that if any component encounters a disruption during data processing, its partner instance can immediately take over, maintaining continuous service availability and preventing data loss. This level of redundancy is one of the key strengths of AMOS. Resilience is built into the application from the moment it is deployed. With the credit default application deployed, we can now use the UI to upload our CSV dataset. As the data is processed, each service updates the graph database, capturing the entities involved, their relationships, and their changing behavior over time. For every month in the dataset, the system tracks each customer's account status, billing information, and payment history, then sends those details to the default service to assess potential risk. Every significant interaction generates its own event vertex, creating a complete temporal record of how the data evolves. When processing is finished, AMOS provides an event-based historical timeline, making it easy to analyze individual customers, trace risky behavior, and understand exactly when and why a potential default is predicted.